Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to go over Riemann sums. But before we really jump into that, let's just do a quick integral introduction, or an antiderivative introduction. When we find the derivative at an exact point, we find the slope of the tangent line. But when we integrate, we find the area over an interval. So when you think of the derivative, think that we're finding the tangent line slope at a point, and for the antiderivative, we're finding the area over an interval. And let's get a good grasp on that. Think back to that relationship of position, velocity, and acceleration. Remember that if we had some position function s of t, well then the derivative of s of t was velocity, v of t. And then the second derivative of our position, or the first derivative of our velocity, was our acceleration function. So in order to help us calculate the speed, we take the derivative of velocity. But if we're given velocity, how far do we know if we've traveled? Can we calculate that if we only know speed and time? Yeah. That's taking the antiderivative, then we'll be able to figure out how far we traveled. And let's take a look at that below. Let's say that we traveled for 4 hours at a constant speed of 5 miles per hour. In order to calculate how far we traveled, we're going to find the area under that curve. So from 0 to 4, I'll be able to calculate this area, and that's going to tell me exactly how far we traveled. You can see that here we have a width of 4, and here we have a height of 5. So multiplying 5 by 4, I'm going to get 20. So we traveled 20 miles. Now this one was fairly easy to calculate because it was just a constant. It was easy to find that area under the curve and to know how far we traveled given our velocity. So given our derivative, we were able to find that area under the curve between the function and our x-axis. And that again was 20 miles. But you can see from the picture we have a nice box. It would also be easy to calculate the area using geometry if we had some other line, because then we could just find the area of a triangle. But think about for a curve. How would we find the area underneath of a curve? Well, that's what we're going to jump into next. For estimating that area under the curve, we're going to use Riemann sums. So again, up above, we had a function that was just a constant, and the area was fairly easy to obtain. But like I stated, what if our function's a curve? The height will no longer be constant, so when we multiply, we're no longer going to be able to do some width times some height, or some length times some height. And since that height is no longer constant, in order to estimate, we're going to break up the area into small rectangles where that height varies. So we have a variable height that we can then use summing those together to calculate the total area. Now I drew the same graph a bunch of different times on this paper so we could talk about just potential different ways to break up our area in order to estimate it. So again, the area of a rectangle is easy to calculate. So we're going to find smaller rectangles that we can use underneath this function. So if I'm trying to find the area under here, let's start by first breaking it up into, let's do 4 separate rectangles. So if I break this area up into 4 individual rectangles, I want the same width for each of my rectangles. So if I have an interval of 2 and I want 4 rectangles within there, well then each rectangle is going to be 1/2 in width. So you can kind of see how I've marked the bottoms of my rectangles below. Now the other thing we need to decide is what is the height of the rectangle, and there's a couple potential options. We can have a rectangle where the top left vertex intersects the function. We could have rectangles where the top right vertex intersects the function, or we can do it where the top middle of our right and left vertex intersect the function. So that's going to be known as left, right, and midpoint Riemann sums. So using 4 rectangles, we're going to first start with our left Riemann sum. So if I'm starting drawing my rectangle and I want my left vertex to intersect my function, I'll start on the leftmost side of my first rectangle, draw that line straight up, and make sure it intersects the function. From there, I'll draw my right side of that rectangle straight up so that it is even with that, and then I'll form my rectangle. So there's my first rectangle. Then the next side starts at 1/2. So I'm going to take that leftmost side and have the top left vertex intersect my function, and then I'll draw up my right side to make it even with the vertex I just drew in order to form that rectangle. And since I'm on the computer, I realize it's going to be easier for me just to make individual rectangles so that I have nice straight edges. But you can see I'm going to make sure that left endpoint intersects my function. So far I have 3 rectangles. I need 1 more rectangle to get a total of 4. And there we can have it. You can see exactly where my rectangles intersect the function, and it's at that leftmost point. You can see that in this case, with my function sloping down, doing that left Riemann sum estimate, my area is going to have a little bit of extra. I'm going to actually overestimate my area. And let's look at if we were to do this with a right Riemann sum. Again, if I want 4 rectangles, I'm going to let each rectangle have a width of 1/2. So from 0 to 1/2, I have 1 rectangle, and if I want that right top vertex to intersect, as opposed to starting at 0, I'm going to start at 1/2 and make sure that I'm intersecting that function. And then I will extend this out to the left side of my rectangle. I'll do the same, but now starting at 1, because that's going to be my right side of my next rectangle. I'll go up to the function and then extend that over. And then for 3/2, same deal. I'm going to go up to the function, extend that over, and then notice at 2, I am touching my function. So my height at 2 is 0. You can see from my right Riemann sum that I'm going to underestimate the area. Look at all this area I haven't even taken into account. So my right Riemann sum, because this is sloping down, is going to underestimate. So the difference between my right and left Riemann sum so far is that my left, I'm using the height of the function at 0, 1/2, 1, and 3/2, whereas for my right Riemann sum, to get the height of my rectangle, I'm using the heights at 1/2, 1, 3/2, and 2. So you can see 0 was included for my left, whereas it was not for my right, and 2 was not included for my left, where it was for my right. Now, looking at midpoint, we're going to do exactly what it says. We're still dividing this up into 4 separate rectangles. Our in value, our subinterval, is 4, and over the length of 2, that's going to give us a width of 1/2 for each of our rectangles. But if I'm going to the midpoint, now I want my height of my rectangle to be at 1/4, then again at 3/4, then again at 1 1/4, and then 1 3/4. Those are the heights of my rectangles at those midpoints. So no longer the left vertex or the right vertex, but directly in between them is going to be the height of my rectangle. So quickly sketching this, and for the sake of time, I'm freehanding this, but I definitely recommend using some sort of straight edge, or if you're on a computer, using that rectangular shape tool so that you can get nice, even rectangles. But you can see for this, we have a little bit of overestimating in some parts, but then underestimating in other parts. And it all depends on the shape of our function. So the difference between left, right, and midpoint is now my heights. Even though I still have those 4 rectangles, my heights are now, like I stated before, at 1/4, 3/4, 1 1/4, and 1 3/4. Those are now my heights. But notice that in each of these, the width of each rectangle is the same. It's that width of 1/2. So if I was to calculate the area, I'd multiply 1/2 by my height, and then add that to my width of 1/2 times my height, and then I do that 2 more times to get my 4 individual areas, and then I sum them together. We're going to get into that in our example, but right now I'm just going over the setup. Also note that we don't always necessarily have to break it up into 4 subintervals. We could only have done 2 subintervals, and if we're doing this with a left Riemann sum, 2 subintervals, that would have a width of, since our interval is 2, if I have 2 rectangles in here, each will have a width of 1. And you can see here is that estimated area, each of those rectangles, which looks less accurate than when I used 4. Let's say that instead of using 4 now, we doubled that amount. So let's use 8 rectangles. If we were to use 8 rectangles along this subinterval of 2, what would the width of each rectangle be? 2 divided by 8, that interval divided by the number of subintervals we want, is going to give us 1/4. So now each rectangle is going to have a width of 1/4. So now you can see that if I used my left Riemann sum, my area is going to be even more accurate. Look how closer those rectangles are to the actual height of their function. There's a lot less overestimation, even just doubling that. And then if you can envision, if I split each of those rectangles up, dividing each of those by 2, having now 16 subintervals, that's just going to get closer and closer and more accurate to the actual area under my curve. And again, this method is known as Riemann sums and is used for estimating that area under the curve, which is our integral. So now actually applying this and going through the methods of calculating the area, for each of the following, we're going to find the area of our function f of x equals x squared over 4 on the interval from 0 to 6, and we're going to use the given methods. So in part A, we're going to use left Riemann sum, where we have 6 subintervals. If we have 6 subintervals over an interval of 6, all we need to do is find the length of that interval. So 6 minus 0 is the length of our interval, and we're going to divide it by the number of subintervals we want. 6 divided by 6 is going to be 1. So each rectangle is going to have a width of 1. So quickly sketching that, using left Riemann sums, I have 1, 2, 3, 4, 5, 6 individual rectangles. And you can see here that with my positive slope, my left Riemann sum actually now underestimates the area. But let's actually calculate the area now. Each of these heights is where our rectangle intersects the function, and each has a width of 1. So because the width is 1, I'm going to multiply 1 by the height and then sum them all together. So you can see our first rectangle has a height of 0. So that's going to be 1 times 0. And then I'm going to sum that to my next area, which is where 1 intersects my function, because that was my left side of my rectangle and I want that left vertex height. So 1, when I enter that into our function is f of x equals x squared over 4. When I plug in an x value of 1, I get 1/4. So I have 0 times 1, my height times my width for my first rectangle, and then my second rectangle has a height of 1/4, and that gets multiplied by the width. My next rectangle, when I plug 2 in, 2 squared is 4, 4 over 4 gives me 1, so that's a height of 1, and it might be helpful if I zoom in just a little bit so you can get a better picture. So that has a height of 1 and a width of 1, and I'll shade these in as I go. Next, I'm on to my height of my rectangle occurring at when x is 3, So plugging 3 into our function of x squared over 4, 3 squared over 4 is 9/4, and I multiply that by 1. Next, I'll do my height, where x is 4, so 4 squared is 16. 16 over 4 is 4, so that's a height of 4, a width of 1. And then lastly, when I'm at an x value of 5, that's the height of my rectangle. 5 squared is 25, so this is going to be 25/4. And that is multiplied by the width of 1. Each of these is the individual areas of the rectangles. If I want that total, I'm going to sum them up. So I'm going to get 0 times 1, which is 0, plus 1/4 times 1, plus 1 times 1, plus 9/4 times 1, plus 4 times 1, plus 25/4 times 1. I'm going to sum 0, 1/4 1, 9/4 4, and 25/4 all together. First, dealing with my whole numbers just to make it easier, 0 plus 1 plus 4 is going to give me 5, and then I'll add that to, now because I have a common denominator of 4, 1 plus 9 plus 25 is 10 plus 25, which is going to be 35/4. Writing 5 with a common denominator, 5 is also 20/4. 20 plus 35 is going to give me 55, and that's all over 4. So my area is roughly estimated to be 13.75. Now I'm going to find the same exact area, except now using a right Riemann sum, and I'm still going to apply that same subinterval. So if I have an interval that has a length of 6 and I want 6 subintervals, that means each width of my rectangle is going to be a width of 1. And using right Riemann sums, when I draw my rectangle, I'm using that right vertex. So right away, I know that my vertex is going to be at 1, 2, 3, 4, 5, and 6 in the x, where up above, it was at 0, 1, 2, 3, 4, and 5. I'm just using that opposite side of my rectangle. So drawing this out quickly, you can see now that using a right Riemann sum, when my slope is positive, I'm going to overestimate. Whereas up above, when my function mostly had a negative slope, my right Riemann sum underestimated, whereas here it's going to overestimate. Let's find the area of each. Each has a width of 1. So when I multiply width times height, if my width is always 1, the area of my rectangle is going to be that height. So I'm just going to write my area directly above each rectangle. And remember, our function is x squared over 4. So the height when x is 1 is 1/4, so that area is 1/4. When I'm at 2, that height of the rectangle is my function value at x equals 2. 2 squared over 4 is going to give me 1. So 1 times 1 is an area of 1. Then at 3, that's going to be 9/4. At 4, that's going to be a height of 4, so 4 times 1 is going to give me 4. Then at 5, that's going to be 25/4, because 25/4 times 1 is an area of 25/4. And then lastly, now 6. 6 squared is 36. 36 divided by 4 is going to give me a height of 9. Height of 9 times width of 1 has an area of 9. Now I just sum those areas together. Again, I'm going to start with my whole numbers. 1 plus 4 is 5. 5 plus 9 is going to give me 14. And I'm going to be adding that to 1/4 plus 9/4 plus 25/4, which is going to be 35/4. Writing 14 in terms of fourths, that is 56/4. So 56/4 plus 35/4 is equivalent to 91/4, which gives me an area of 22.75. So up above, I had an area of 13.75. This was an area of 22.75. Let's see what happens when I do a midpoint Riemann sum. Again, my subinterval of n is 6, and that means that my individual rectangles are going to have a width of 1, because if my interval goes from 0 to 6, that's a width of 6 for my interval, and if I want to split that up into 6 individual rectangles, that's a width of 1 per rectangle. And now I want my midpoint to intersect. So zooming on in, my midpoints are going to be 1/2, 3/2, 5/2, 7/2, 9/2, and 11/2. If those are the heights, I'll quickly draw out each of my rectangles. And there we go, there's a rough sketch of each. Remember, each still has a width of 1. So with that width of 1 and multiplying it by a height, the height is going to be the area. So I'm going to enter in 1/2 into my function, 3/2, 5/2, 7/2, 9/2, and 11/2, and calculate each of those. So going through that quickly, my first rectangle has an area of 0.0625, and I'll add that to my next rectangle, which has an area of 0.5625, and then I'll add that to, so far I've calculated my 2 rectangles. Now my third rectangle, an x value at 5/2, when I plug that into my function, I'm going to get 1.5625, and then I'm going to add that to my next rectangle, which has an area of 3.0625, and then I add that to my next rectangle, which has an area of 5.0625, and then that gets added to my next rectangle, which has an area of 7.5625. Summing all of those together, that's going to be equal to 17.875. Or if you calculated this using fractions, because each of these is a half, when I square it, I'm going to get 4 in my denominator, and 4 times 4 is going to be 16. So each of them will have a common denominator, and that's eventually going to simplify down into 143/8. I just thought it might be easier to write it as decimals so you could see how that 17.875, that midpoint Riemann sum, fell between my area for my left Riemann sum and the area I calculated for my right Riemann sum. And like I stated before, the only way we're going to get a more accurate area is if we split the overall interval up into smaller subintervals, essentially decreasing the width of each of my rectangles. So now if I want 12 rectangles, I'm still using that same interval from 0 to 6. Remember, that interval has a width of 6, and if I want that divided into 12 individual rectangles, each rectangle is then going to have a width of 1/2. And I'll go ahead and do this with a left Riemann sum. So now splitting this up into 12 rectangles as opposed to 6, using a left Riemann sum, that's at 0, and then 1/2, and then 1, finally 1 and 1/2, then 2, and so on. So let me finish drawing out these rectangles really quickly, and then we'll calculate the heights, and this time the width is 1/2, so we're going to actually have to multiply width times height to get that area and then sum them together. The previous 3 all had a width of 1, so it was relatively easy. Now dealing with the width of 1/2, we're going to take that into account. There you have it. You can see each of my 12 rectangles. 1, 2, 3, 4, all 12 rectangles. Remember, each has a width of 1/2. So what I'm going to do is I'm going to calculate all of the individual heights, multiply them each by 1/2, and then sum them together. So using left Riemann sums, my first rectangle has a height of 0. My second one, that left vertex when x is 1/2 intersects my function, and that's 0.0625. And then when I use a value of 1, I'm going to get 1/4, or 0.25. And then at 3/2, I again intersect my function, and that's going to be 0.5625. Then again at 2, I intersect, and that's going to be 1. And then at 5/2, that's going to be 1.5625. And then now moving on to 3. Remember that was 9/4, so that's going to have a height of approximately 2.25. Then moving on to 3.5 or 7/2, that was a height of 3.0625. And then moving on to 4, that was a height of 4. And then moving on to 9/2, remember 9/2 has the height of 5.0625. Then moving on to 5, 5 squared over 4, that's 25/4, which is a height of 6.25. Then from 5, I move on to 11/2, and 11/2 gave us a height of 7.5625. And then I don't need 6 because 6 is just the right side of my last rectangle, so I don't continue on. 12 rectangles, you can see here that I have 12 different heights. So if those are the heights of my rectangle, I'm going to take each of those and multiply them by 1/2. So 0 times 1/2 is 0. 0.625 times 1/2 is 0.03125. So 0.25 divided by 2 is 0.125. And then 0.5625 divided by 2, that was using that x value of 3/2. When I divide that height by 2, I get 0.28125, and then 1 divided by 2, that's going to be 0.5, and then 1.5625, multiplying that by a width of 1/2, essentially dividing by 2, that's going to be 0.78125. Then 2.25 divided by 2, 2.25 times 1/2 is 1.125, and then 3.0625 times 1/2 is 1.53125. 4 times 1/2 is 2. 5.0625 times 1/2 is 2.53125. 6.25 times 1/2 is 3.125. And then lastly, that 7.5625 times that width of 1/2, so height times width of our last rectangle, is going to give us an area of 3.78125 for that last rectangle. So each of those is the individual areas of my rectangle. So if these were the heights, I multiplied that by 1/2, which was my width, and that's going to give me area. Now all that's left is to sum each of these together, which when I sum all of these together, that's going to give me an area of approximately 15.8125. So looking at D with an area of 15.8125 for the estimated area versus A where we got an estimated area of 13.75, I know that the exact area is actually 18. So that 15.8125 was a lot closer than when we did the left Riemann sum with a subinterval of 6. Now imagine if we did a left Riemann sum with a subinterval of 24. So each rectangle would have a width of 1/4. So you can envision as we increase that subinterval, we're going to get a more and more accurate picture because the rectangles are going to match the height more closely, and zooming back into D, we won't have as much missing, or we won't have as much overestimation depending on whether we're using left, right, or midpoint Riemann sums. And you may ask me, how do I know that the actual area is 18? Well, that's by actually setting up an integral and integrating this, because remember the integral is going to give us the area between our function and our x-axis, which in this case, we're going to have the integral from 0 to 6 of x squared all over 4, and we're going to integrate that with respect to x. Later, you're going to learn how to actually do this and understand the exact setup that I have here. So make a note of this and come back to the worksheet and double check that area of 18 once you learn these strategies. But with this last example, we'll wrap the worksheet up here. So continue on to that next worksheet where we're going to learn more about integrals, going into a definite integral and actually trying to understand how to find that exact area as opposed to just estimating. So continue on, but until then, good luck with your online learning.